So today's lesson is on limiting/excess reactants. You also will hear that called limiting/excess reagents. Reagent and reactant stand for the same thing for our classwork today. So we're going to understand what a limiting/excess reactant is, and then we're going to determine both the limiting reactant and the excess reactant. The simplest definition of a limiting reagent/limiting reactant is the material, the reactant, that is used up first in a chemical process. It limits the amount of product that can be produced. The limiting reactant can define the overall yield of the process, and then anything that's remaining is determined to be the excess reactant or the excess reagent. It's no more complicated than that. So whatever you run out first, that limits how much of the other stuff you can make. Okay, so let's see if we can come up with a concept of limiting excess reactant reagent using the following scenarios. I want to make cheese sandwiches, and I go into my refrigerator and I find I have 8 pieces of cheese. And I go into my cupboard and I find I have 24 slices of bread. I want to know how many sandwiches can I make and what material runs out first. So here's my recipe. It says for every sandwich I require 2 slices of bread and 1 slice of cheese. So if I was to write the ratio for this, it's 1 cheese for every 1 sandwich. And if I was to do it for the bread, it's 2 breads, 2 pieces of bread for every 1 sandwich. So the ratio is 1 to 1 here and 2 to 1 here. Okay, so now I'm going to go back and look at my cheese. It says I have 8 slices. So for every slice, I can make 1 sandwich. So at the end of the day, the amount of cheese I have, the maximum amount of sandwiches I can make would be 8. I have 24 slices of bread though. Wow, that's a lot of bread. But I require 2 slices of bread for every sandwich. So for every 2 slices of bread, I'm going to need to make 1 sandwich. So I can only make 12 sandwiches now because 12 times 2 is 24, and I'm going to run out then of bread. So now which of these do I run out first? Well, you can see that I'm going to run out of my cheese first. So the cheese is my limiting reagent. And what do I have extra of? I'm going to have extra bread. And so that would be my excess. Because it says I can make enough sandwiches with the bread for 12 if I had enough cheese. And here it says I can only make 8 sandwiches even if I had excess bread because I'm going to run out of cheese. So that's what I mean by limiting an excess reagent. And you could do the same thing down here with the frames, right? 10 car frames and 16 wheels. So it says to me that 1 frame is necessary for each car. So if we were to do this, it's 1 frame per 1 car. And then over here it's 4 wheels per 1 car. And then if you did the math and you looked at your thing, you had 10 car frames, so you could make 10 cars. And here you would only make 4 cars because 16 wheels divided by 4, because 4 wheels per car gives me 4 cars. So again, what is my limiting? In this case, it's the wheels. So that would be my limiting. And then what is my excess? That would be the frames, and that would be my excess. So there you go. That's kind of a quick scenario or tutorial on limiting and excess. One of the things that's going to run out, whatever that thing is, limits how many of the product that you can make because it runs out. Now, before we go into the criteria that's necessary to use BCA tables to solve these types of equations, I want to let you know that when you run a chemical process, almost always one of the materials will run out first. No matter if you're very careful about loading the reactor with exact amounts, something always runs out first for a variety of reasons that we're not going to get into. So be aware of that. Now, the other thing that you're going to need to know is that there are some skill sets that you're going to have to know how to do before you tackle the rest of the short tutorial here. You've got to be able to balance chemical equations, know what the mole ratios are from balanced chemical equations, calculate moles from grams and grams to moles if necessary. Familiar with the BCA tables, before, change, after, and how to use them, and then how do we do stoichiometry problems using BCA tables. I'm not going to spend a lot of time going over all this stuff here, so these are skill sets that you're going to need to move on for the rest of the video. So this should look very familiar from here. It's a BCA table again. Remember, before is what you start with. Change is what's happening during the reaction or the process. And then after is what you are left over with, or at the end of the day, right? If you fully consume something, the after will always be 0. If you're starting afresh with something, and the products are generally 0. So there's going to be a couple of zeros possibly on here. The change is what you're going to be calculating. Alright, so let's see how we use the BCA tables to help us solve limiting and excess reactant problems. First step is we have to look at and make sure that we have a balanced chemical reaction. So do we? So let's see here. What is the limiting and excess reactant if 4.2 moles of magnesium is reacted with 5.8 moles of HCl? Well, so we don't have a complete chemical equation, so I'm going to write one. And I've written one right down here, right? So you may have to write one, hopefully not, but if you don't have to write one, make sure it's at least balanced. And then I balanced it, so it says that 1 mole of magnesium solid reacts with 2 moles of hydrochloric acid to give me 1 mole of magnesium chloride solid and 1 mole of hydrogen gas, okay? Now, the next thing you're going to do is you're going to pick one of your reactants as being the limiting reactant. It does not matter which one. You can pick either one. If you had 3 reactants, you could pick one of the 3. Some people like to pick the first one. Some people will like to pick the last one. Some people, like me, pick the one with the smallest amount of moles. Whatever, right? It doesn't matter, because at the end of the day, the math will tell you if your prediction is right. The math will also tell you which one is the limiting reagent and which one is the excess reagent. So there's no wrong way to do this. There's no wrong pick. That's what I'm trying to say. So I'm going to say we're going to pick this one, magnesium. I'm going to say that's my limiting, and then this is my excess. Okay? Now, we fill in the blanks with all the information we know. So here we go. That comes from here. This comes from here. And we don't have any product made yet, so we fill in that. So this is before. And the last step as we do is, before we do any calculations, we have to look at the molar ratios of every product and every reactant based off of the material that you have chosen as the limiting reagent. So here's my limiting reagent, so magnesium, so it's a 1-to-1 ratio. 2-to-1 for this one, because again, we're referencing magnesium as the bottom. That's my reference point. So it's 2 HCl's for every 1 magnesium, 1 magnesium chloride for every 1 magnesium, 1 mole of H2 gas for every 1 mole of magnesium. So now that I have these molar ratios, I'm going to be using these in the calculations on the next page. Okay, so now that we've done that and we've picked our one that we want to have as our limiting reagent, we fill in the blanks we did. Now remember, the limiting reagent is going to get all used up. It's going to run out first. So I'm going to assume that I'm going to use all of that. So I'm going to put this value in here, and at the end of the day I'm going to have 0 moles of magnesium left. Remember, we said that this was my limiting. Okay? So it's going to run out, and it's going to be all consumed. Now, we don't know yet how much HCl we're going to have to use to consume all that magnesium, but we will in a minute when we do the calculations. And we don't know how much of the MgCl2 and the H2 we're going to make. I've copied all the ratios here to help us do the math, right? Now, when you calculate the amounts of materials needed, you're going to do that using the ratios here. So let's look at how we're going to calculate how much HCl. It says here for my ratio, for every 1 mole of magnesium that I use, I need 2 moles of hydrochloric acid. So I'm using 4.2 moles, so I need to double that. So I'm going to put here minus 8.4. Right? And then I'm going to do the same thing here. It says for every 1 mole of magnesium chloride I want to make, I need 1 mole of magnesium. So this is a plus 4.2. And this is also a plus 4.2. These are all moles. I just ran out of room to write that. So why is this minus and this plus, right? Because we're consuming this, we're getting rid of it, we're using it up in the reaction, and we're making these things. So we're adding and we're removing. That's what the convention means. Okay? So now let's go on to the next page. Okay, once you've finished filling in the change, then you add up the before the change to give you the after. So 4.2 minus 4.2 is 0. 5.8 plus negative 8.4 is minus 2.6. And you're like, what? That doesn't make sense. So we'll go back to that in a second. 4.2 plus 0 is 4.2. 4.2 plus 0 is 4.2. Now, you're looking at this and saying, well, it says here I'm going to be minus 2.6 moles of HCl. I can't have minus matter. So what does this really say? This really says that you don't run out of Mg first. You actually run out of HCl first. Why? Because you're deficient. You are negative. Because in order to fully consume all of this, you would need 8.4 moles of HCl, but you only have 5.8. So once you get down to the 5.8, once that's done, you don't have a reaction anymore. It stops. So you would have not fully reacted all this. So this limits, and this is my excess. So even though we picked that magnesium was my limiting reagent, at the end of the day, we now know that our prediction was, quote, incorrect, but we now know the correct answer. The correct answer is HCl versus magnesium. The HCl runs out first. Okay. So now that you've got this, you now know, you can answer the question, which one is the limiting and which one is the excess, and you have that answer right here. So you would say that the limiting is the HCl and the excess is the magnesium. Now what happens if it said, what is the theoretical yield? Well, you can't use these numbers here because, remember, that assumes that you used 8.4 moles of it. You didn't. So you have to go back and recalculate using the correct values now. We're going to do that on the next page. This will make a little bit more sense once you see the next page. Okay, so if the problem then asks you how much or what is the limiting reagent and how much extra of everything else do you have, you may have to go do a second iteration on this. Now that you know which one runs out first, now you know what to base that off of. So we're going to do everything exactly the same, except we know that this is my limiting reagent. So we know we're going to have excess amount of this left over, and we're not going to make a lot of this as much as we did before because this is going to limit how much we can make. So again, we go through and make our ratios, fill in the information you already know in the appropriate boxes. Again, everything's the same, except this time we're going to use all of the HCl. It's going to run out, and then we're going to see how much magnesium we need to do that. Okay, so this is the last slide. So let's see how we can do this. So we used up all 5.8 moles, so we have 0 moles there. That's my limiting. That's what the red thing means. Now let's go back to our ratios. Our ratios said that we use, for every 2 moles of HCl, I only need 1 mole of a magnesium. And I only make 1 mole of magnesium chloride. And I only make 1 mole of hydrogen. So you're going to divide everything by 2, this number by 2. Why? Because it says for every 2 moles of this, I only need 1 mole of this. So for every 1 mole of this, I make 2 moles of this. So it's the ratio is 2 to 1, right? So I'll divide everything by 5.8. Excuse me. I divide 5.8 by 2 to get me the amount of magnesium. That's how much I'm going to use. Not 4.2, only 2.9 moles. And I'm only going to make 2.9 moles of each one of these things. So at the end of the day, when I do that, I have 0 moles of HCl left. I have 1.3 moles of magnesium left. And I have made only 2.9 moles of magnesium chloride and 2.9 moles of hydrogen. So now that you have this, and there are no negative numbers here, there can never be a negative number here if you want to do the theoretical yield, right? If you have a negative number, you can't use the numbers here for a theoretical yield, because that means that you ran out of material before you made the proper amount. So, okay, now good. So now we have 0, 1.3 is positive, 2.9 is positive, 2.9 is positive. So this is how much you have excess. And this is the limiting amount of material that you can make. This is your theoretical yield. So this is how much excess. This is the limiting reagent. And your theoretical yield is only 2.9 moles. That's it. Okay? Again, so if you have a negative number here, these numbers can't be used for the theoretical limit. Only if this number is 0 and everything else is positive can you use it. And remember, the theoretical yield is the maximum you can make per that reaction before the limiting reagent runs out. So once the limiting reagent runs out, you can't make any more stuff. There's no more stuff to be, there's no more raw materials to make it. Okay. So why do we spend a lot of time talking about limiting and excess reactants, when in reality, most of you will not go into a chemistry environment, a chemistry lab, and have to worry about this on a chemical scale? Well, here's the reason why. In most commercial applications that make products that are tangible products, something that you would sell and you can hold, so things, it costs money to buy raw materials. It costs money to QC those raw materials when they come in the house. It costs money to manufacturing those materials into a new component or thing. It costs money to QC that. And then it costs money to store this in a warehouse, right? All of that costs money. So most things are made on demand. What I mean by that is you have an order that comes in for 100,000 light bulbs. Most places don't have 100,000 light bulbs just sitting in their warehouse. They'd have to make them, right? So they have to order all the raw materials. They may have some materials left over from a previous run, and that's good information to know, because if you said, well, which one of those is going to run out first, so I've got to make sure I order that, that's when this stuff comes into play. Think about ordering like a large Boeing or Airbus airplane. You just don't go down to the Boeing or Airbus showroom and they don't have a bunch of planes lying around saying, hey, I want to get 3 747s today and I want 2 757s. Give me a 767. Oh, and I want that 787 too. And can you deliver it tomorrow? They don't have them. They've got to make them, right? So they've got, and they might have inventory of other things already purchased for similar airplanes that they can use. So they have to know how much of each to buy. And that's where the limiting and excess reactant process or technique or concept comes into play. So it may not seem like this is tangible in life, but it's very tangible when you go out into the manufacturing world and actually have some inventory. You want to know how much of the other stuff you have to buy, or how much can you make knowing the inventory that you have. That's why we teach it.